Our project is question answering with transformers. Machine question answering is an interesting NLP task which measures machine reading comprehension. It is important because, in a way, it measures how well a machine or a deep learning model understands a piece of text. Transformers are a great NLP architecture for encoders and decoders which uses self attention and convolution instead of traditional RNNs or LSTMs. The question answering problem, from our purposes, is stated as having a context, which is a passage, a question, which may or may not be answerable, and the answer has to come from within the context. It's a span, or it might not be answerable. We use a squad data set by Rajpukar and others. It consists of more than 100,000 questions crowdsourced from Wikipedia, and it is an excellent data set for testing question answering models. Here's an example of what it looks like: a question, a passage, and the answer from the context itself. We use the QANet model proposed by Wu and others. Um, so this has the idea from the transformers, which replaces the traditional RNNs and LSTMs um, uh, with convolutions and self-attention, and the main purpose is to make it more parallelizable on GPUs. This is an overview of the model. It consists of 4 layers, which we'll get into, and a workhorse encoder block on the right. Here we describe the encoder block. This consists of 4 layers. Firstly, the position encoding, which is important. It's a sinusoid encoding, and this is needed because in normal LSTMs or RNNs, we have a notion of sequence. But since we're using only convolution, we don't have that notion. So we need a sinusoid, multiple sinusoids to encode the position so that we get a notion of sequence. We have a 1D convolutional layer, which may be repeated a number of times. We have a self-attention layer, which is a multi-headed self-attention proposed by Vaswani and others in the Transformers paper. This allows us to have attention at different parts of the question and the context at the same time. And then we have a traditional feed-forward layer. Each of these layers have layer normalization applied to them, and also, they also have a residual connection directly from input to output, which improves performance. Some few more details on the layers. We have from bottom to top, we have an input encoding layer. This consists of 300 dimensional glove vectors, learnable character embeddings, parts of speech embeddings, which we'll talk about later, which is not part of QNet as such. And these are encoded using the encoder block we saw before, consists of 1 encoder. Then we have the context query attention layer, which is from CO and others from the BIDAF paper. We then have the model encoding layer, which is 3 encoder blocks. Each encoder block consists of 7 encoders that we saw earlier. The encoders are stacked in the way shown. The next layer is the output layer, which uses a linear transformation and softmax. We predict the start probability using the bottom output of the bottom 2 encoder blocks, and the end probability using the top 2, the bottom and the top encoder block. And the predicted span is the one which has the maximum probability of the multiplication of the starting and the ending probability. We also restrict spans. We only consider things of a maximum length, and also some innovations we'll talk about in the next slide. So we just talked about the traditional QANet model. We have some additions to it. One is the parts of speech tagging. We use the NLTK library. This slide shows an example. For example, in the sentence Charles W. Eliot, etc., Charles is an NNP or a noun proper singular. Eliminated is a VBD or a verb past tense. We have 45 of these tags. They are embedded and learned in the model. We also introduce discounting probabilities of larger answer spans, because we found that our model was predicting larger answers instead of shorter answers. And most of the answers were short, so we thought it'd be nice to discount the probabilities of larger answers over smaller answers, and that gave us a little bit of a boost. We tried using fast text embeddings, which has been shown to be better than glove embeddings, but we could not use it to our benefit, so we did not use it. So a significant challenge of this project was the resources. We did not have a very fast GPU. We had half of a Tesla M80 GPU, which prevented us from scaling the model. QNet, we chose QNet mainly because it advertised great speed, but we found that it ran actually much slower, mostly because we could not fit the model into the memory, so we had to use very low batch sizes. And in fact, it ran slower than the baseline BiDef LSTM implementation. So to alleviate the resource crunch, we ran experimentation on a very small scale. So we reduced the encoder blocks, number of encoder blocks, the hidden size, the embedding size, and we ran various experiments. Here's an example of a few. For example, we tried fast text, the positional embeddings, character embeddings, and we used this to figure out which ones we should run with a bigger model. Here are results for the bigger model. Uh, as you can see, we spent a lot of time running these models. It took over 21 hours. And we got a F1 of 63.92 at the end, and exact mass score of 60.65 for all the features that we had. We could run very less of these big models because of long training times, which turned out to be very expensive. So the major future work for this should concentrate on optimizing the memory model so that we can use a larger batch size. We should also consider optimizing the parallel processing to take advantage of the QNet architecture, which should be more parallelizable than the LSTM based architectures. State-of-the-art models today use pre-trained contextual embeddings like BERT. We'd definitely like to experiment with that. I'd like to give thanks to the papers we use: QNet by Wu, Squad by Rajpukar, and BiDef Attention Flow by CO, and also many thanks to Chris from the TAs who gave us excellent starter code, which was extremely helpful. Thank you.